Till now in connectivity, I already discussed what is path, what is circuit, how to check one graph is connected or disconnected, what is caught edge, caught vertex, edge connectivity, vertex connectivity, strongly connected, weakly connected, strong component. Next I will discuss some more properties about connectedness. Theorem 2, a simple graph G with n vertices is necessarily connected if number of edges is greater than n minus 1 multiplication n minus 2 divide 2 and necessarily disconnected if number of edges is less than n minus 1. Let's take an example. Suppose n equals to 3. We have 3 vertices A, B, C. So it will be necessarily disconnected if it is less than n minus 1. So if number of edges is less than 2, then it is necessarily disconnected. Less than 2 means it can be 1. Suppose there is just one edge, then it is disconnected. A is one component, B, C is another component. Now it will be necessarily connected if number of edges is greater than n minus 1 multiplication n minus 2 divide 2. Here n equals to 3. So 3 minus 1 multiplication 3 minus 2 divide 2. 2 multiplication 1 divide 2 means it should be greater than 1. Number of edges should be greater than 1 means at least it can be 2. If there are 2 edges, then it is connected. Let's see one example. Example 11. Which of the following simple graph is connected? Option A graph with 10 vertices and 30 edges. So number of vertices equals to 10, n equals to 10 and number of edges equals to 30. 30 should be greater than 10 minus 1 multiplication 10 minus 2 divide 2. 10 minus 1 is 9 multiplication 8 divide 2. So it's 36. Is 30 greater than 36? No. Hence this graph is disconnected. Next option B, a graph with 9 vertices and 28 edges. So 28 should be greater than 9 minus 1 multiplication 9 minus 2 divide 2. 9 minus 1 is 8 multiplication 7 divide 2. 8 divide to 4. 4 multiplication 7. It's 28. 28 equals to 28. That's why it may or may not be connected. It's not sure that it's connected. Next option C, a graph with 8 vertices and 22 edges. 22 should be greater than 8 minus 1. It's 7 multiplication 8 minus 2. It's 6 divide 2. So 6 divide 2 is 3, 7 into 3, it's 21. 22 is greater than 21, hence this graph is connected. So for connected, it must be greater than n minus 1 multiplication n minus 2 divide 2. If it's equal, then it may or may not be connected. And if it's less than, it's surely not connected. Now example 12, the minimum number of edges required to ensure connectivity with 7 vertices. So we have 7 vertices. How many edges required to ensure connectivity? So 7 minus 1 multiplication 7 minus 2 divide 2. 7 minus 1 is 6, 7 minus 2 is 5 divide 2. So 6 divide 2 3, it's 15. For surely connectivity, number of edges should be greater than 15. Means minimum number of edges required to make sure that the graph is connectivity with 7 vertices is 16. Now some properties of graph. A simple graph with n vertices and k component has at least n minus k edges, and a simple graph with n vertices and k component has at most n minus k multiplication n minus k plus 1 divide 2 edges. So number of edges lies between n minus k and n minus k multiplication n minus k plus 1 divide 2. So at least it should be n minus k and at most it should be n minus k multiplication n minus k plus 1 divide 2. Suppose it's a connected graph. In case of connected graph, number of component will be 1. Now number of edges should be lies between n minus 1. In place of k, I am writing 1 less than equals to number of edges which is less than equals to n minus 1. Then n minus 1 plus 1 minus 1 1 plus 1 will be cancelled. N divide 2. In case of connected graph, number of edges lies between n minus 1 and n minus 1 into n by 2. This is the number of edges in case of complete graph. Let's see some examples. Example 13. Minimum number of edges in a simple graph with 10 vertices and 3 components. So here n equals to 10 and k equals to 3. Minimum number of edges equals to 10 minus 3 is 7, and maximum number of edges will be 10 minus 3 multiplication 10 minus 3 plus 1 divide 2. 10 minus 3 is what? 7 multiplication 7 plus 1. It's 8 divide 2. So minimum number of edges is 7 and maximum number of edges equals to 28. Next example 14. Let G be a simple graph with n vertices and k component. If you delete an edge in G, then the number of component in G is k or k plus 1. Suppose that edge is the caught edge, and after removal of caught edge, number of component may be increased. So it will be k plus 1, and if that edge is not caught edge, then it will be same. So number of component after deletion of the edge will be simply k. Next example 15. Let G is a simple graph with n vertices and k component. If we delete a vertex, then number of components can be between k and n minus 1. K if that is not a caught vertex, and it will be n minus 1 if that is a caught vertex and the graph is a star graph. What is star graph? In star graph there are multiple vertex, and in between all there is another vertex, and this vertex is connected with all other vertices. So this is an example of star graph. If we will remove this middle vertex and all its adjacent edges, let this is A, B, C, D, E, F, and this is G. If we remove G and all its adjacent edges, then this will be disconnected, and how many component will be there? There will be n minus 1 component. In this graph there are 1, 2, 3, 4, 5, 6, 7 vertices, n equals to 7. If we remove G vertex and all its adjacent edges, now there are 6 components. So all these individual vertex are 1 component, so there will be n minus 1 component in case of star graph. So the number of components will be in the range k and n minus 1. So maximum it can be n minus 1, minimum it can be k. With this I am finishing connectivity. In next lecture I will discuss Euler and Hamilton path. If this lecture is helpful for you, please like, share and subscribe. Thank you.